All right, everyone. So welcome to the first part of the homework in our heat transfer portion of the class. For this video, I'm going to be working on deriving the heat diffusion equations for Cartesian coordinates and for spherical coordinates. So we're going to go ahead and do that, and I'll walk you through it. First, I want to start with something I have up here. So this is going to help us to conceptualize the problem. So we're working with the heat diffusion equation first in Cartesian coordinates. So the way we want to think about that is, let's think about a differential volume that I have drawn here. So an infinitesimally small volume, and I've drawn what that would look like, where the x-axis would be dx, y is dy, and z is dz. And what this defines is our control volume, or our infinitesimally small volume. Because it's our control volume, it's also our differential volume. So this is how we want to conceptualize it. That way, we can describe energy passing through a medium like this. So you'll notice, first off, there's a lot of arrows going in and out. And so let's define what each of these arrows is talking about. So we have three arrows going in. So I have my qx, my qy, and qz. And that's the energy heat rate going through this medium as an input. So this is energy that's going in. Qx, Qy, Qz. It's going into this control volume. And you'll see opposite of that, coming out, there's three arrows pointing out, and they're labeled as Qx plus dx, Qy plus dy, and Qz plus dz. And what this is describing is the energy that's coming out of the system after it has passed through this control volume. So for each one of these axes, then we have a corresponding output control or output energy rate transfer, and it will be modified by some stuff going on here. So the other two things to notice from this control volume is there's an EST and an EG here. And so what those stand for are EST is my energy storage term, and my EG is my energy generation term. And the reason I have those is because we're going to solve or derive this equation of heat transfer, or heat diffusion rather, from our conservation of energy equation. So let's go ahead and write that so you can see why I have all these terms here. So if we think about it, we have energy going into this medium. And we know that energy has to be conserved. So we can write, first off, energy going in has to equal energy going out. Energy going in has to equal energy going out. Now that's really simple, but there's a couple other things that could be happening that we have to add into this equation. And one of those is energy could be stored. So think about it, if this energy is going into this, and some of that energy is not going to be going out, but will actually be being stored within the medium itself as it heats up. And so not everything is going to go out, but there may be some actual latent energy stored in this medium. So let's add that, knowing that, let's add that to our equation. That our energy in minus any energy that we stored, because we're losing that into the medium, has to equal our energy out. All right, so we're almost there for our equation. There's one other thing, though, that we have to think about. Sometimes, depending on the medium and depending on the problem, we can actually have energy being generated within the medium itself. So the example given in class was like concrete. While it's settling into its form, it actually is outputting some energy. So if you think about it, we might lose some energy being stored in the medium, but if there's any energy actually being generated within the medium, well, we need to describe that too and think about it in our equation. So let's write that final term here into our overall energy conservation equation. So energy in minus energy stored, which is any energy that we're losing into that medium, well, plus any energy generated, because we're gaining a little if we're generating some, plus any energy generated, equals our energy out. And so there we go. We have all of our terms here in the conservation of energy equation. I probably will be rearranging that so that when we do some summing in and some algebra later, it'll be a little bit easier. But this is the correct equation right here. And we've compensated for every term. So once again, this is our control volume. It's infinitesimally small. It's a differential volume. We have energy going in, described by our Qx, Qy, Qz. And we have energy going out, described by our Qz plus dz, Qy plus dy qx plus dx. Those energy going out terms are going to be modified by what's going on in this medium, which is energy stored and energy generated. They will modify each of these q's, and they will vary according to what's happening in the medium. So that's how we're going to think about our problem. I'm going to go ahead and get into the actual mathematics of it now and start putting in some terms and describing this a little further. So let's go ahead and do that. All right, so first let's talk about these energy outflow terms, the arrows that we had going out of our differential volume there, our control volume. So let's think about a different way we can express that, which is going to be useful to when we are solving for our heat diffusion equation and plugging everything into our energy conservation equation. So let's think about this. This is just saying our heat transfer rate, our energy outflow at location x plus dx. All right. So if we think about that, we can write this in this way, and I'll explain this. That's going to be equal to our, it's going to be equal to our heat transfer rate at x, all right? Now, plus the amount it changes by inside that medium. So that's going to be the amount it changes by, the change in qx, and we're talking about in the x direction, times x, all right? Times the x it's allowed to change over. Now, this is a little bit hard to conceptualize at first, so let's not think about it in terms of heat. Let's think about it, say, in terms of speed, all right? So if this is some speed at location x plus dx, we can think of it, what's that going to be equal to? Well, it's going to be equal to the speed we had before, the speed we were going into this volume, plus, let's think of this term right here, this complicated differential. Let's just think of that as like an acceleration, all right? So this is the amount this speed is changing by per time, say. And then, of course, we're going to multiply that by the amount of time it's allowed to change over. So putting that together, the speed going in would be equal, or the speed going out would be equal to the speed going in, plus the acceleration times the time. That is the change of the speed over time times the time it's allowed to change over. And so you see, it's not too hard to conceptualize. It's only because we're dealing with heat, which is a little bit more abstract concept, that it's not as intuitive. But it's the exact same logic. So this is just, when we look at this, actually just we were doing a Taylor series expansion, neglecting higher order terms for these terms. And that's all that we're doing. It's intuitive once you put that sort of logic to it. So I'm going to do that for the rest of these right here. Qy plus our change in Qy over y times the y it's allowed to change over. All right, and of course for z as well, our qz plus our change in qz with z times the z it's allowed to change over. All right, so that's how we're going to express these outflowing arrows, and we're going to find that these are actually really helpful for canceling out some stuff when we actually go to our energy conservation equation. And yep, so that's all that there is for that. Let's go ahead and get to the next part. Let's now take care of, well, first off, let's just think, we'll leave qx, qy, and qz as they are right now. So we'll elaborate more on those later, but let's just leave those as qx, qy, qz right now. Some arbitrary heat transfer rate going in. And we will do more with those later. But first I want to focus on our energy storage and energy generation terms. Let's describe those real quick. So I'm going to erase this. All right, so let's talk about our energy storage term first. So if you remember from Physics 1 or some earlier physics class, we talked about energy. And one of the things that we talked about was the energy is going to be equal to our mass times our heat capacity times our change in temperature. That's the general equation that we're working with. And so let's use that thinking for our energy storage, okay? So our energy storage term, how are we going to describe that? How are we going to describe it? Well, we can think of it as, first we need a mass. Well, this control volume will have some density, all right? Some density rho. And of course, a density times the volume is going to be equal to a mass. So let's just multiply it by the volume. Well, what's the volume for this? It's a cube. dx, dy, dz multiplied times each other. Those are my three axes. And that'll give us our volume. So let's go ahead and do that. dx, dy terrible x, dx, dy, dz. All right, so this right here is just my mass, all right? Now, heat capacity, we don't really have to do anything special with that. We'll just have some arbitrary heat capacity, whatever it is, depending on the medium. And then my change in temperature, well, that's easy too, because that's just going to be my change in temperature, which is a partial of T with respect to time, my change in temperature with time. And so right away we see this is our energy storage term, and it's going to be useful in deriving our heat diffusion equation later on. Finally, let's talk about our heat generation term before we get to our Qx, Qy, Qz. This one's even easier, our energy generation. Well, there's not much we really can do with that, so we'll just say it's equal to some heat transfer rate, arbitrary Q dot, and it's just times the control volume, once again, dx, dy, dz, and this is just saying this is the amount of the heat transfer rate per unit volume multiplied by the volume, and so that's how much energy we're generating in this control volume. And so that's all we have to do to describe E sub g there. So now that we've defined our energy storage term, our energy generation term, we've expanded our QX's plus DX, our outflow terms. We've expanded those into more useful nomenclature. Now I think we're ready to work with our QX, our QY, and our QZ. And what we're going to be doing is using Fourier's law to put a little bit more of our problem into these before we get into summing everything back into our energy our energy conservation equation. So we're going to go ahead and do that right now. All right, so I actually decided we're going to write out our energy conservation equation with the terms we have now first, so it'll be a little bit more helpful to see why and when we're using Fourier's law. So let's go ahead and just write out everything, and then we will get to Fourier. All right. So I told you we're going to rearrange that energy conservation equation that we had to begin with. So let's write it out here. And I want to set everything equal to my energy storage term. All right. So my energy N, all right, plus any energy being generated, minus any energy being stored, is going to be equal, of course, to my energy going out. All right. Energy going out. All right, now let's rearrange this. So my energy going in plus energy generated minus energy out, moving it over to the other side, is going to be equal to my energy being stored. All right, so this is our general equation. Now let's plug in the terms we just defined into this equation. All right, so what's my energy going in? Well, for right now, let's just use Qx, Qy, and Qz. Those are my energy terms that are going into the control volume. So let's add those all up. And that'll be my energy in. Qx plus Qy plus Qz, all of my heat rates going in. Now, my energy generation term, we just described that, and that's going to be equal to some arbitrary generation rate time per unit volume times our control volume. All right, we just talked about that. Minus my energy going out. Well, we described our energy out terms using our Taylor series expansion. So we'll just now add all those up, or rather, seeing that this is being subtracted, each of those Taylor series expansions are going to be negative because we're subtracting them once they're added together, which means we're subtracting them all from this. So let's go ahead and do that. So for my x, it would be minus qx plus partial x with respect to would be my qx plus my change in x. Sorry, this should be my change in temperature with x times the with x times the x is allowed to go over. And once again, this minus sign is distributed to each of these terms in the expansion. So we'll go ahead and do that. It'll be a little bit lengthy, but I think we'll be fine. We'll do that for each term now. Minus qy minus my change in temperature with respect to y times the y changes over minus qz. Change in temperature with respect to z. Oops, not a q, that's a delta. Z is allowed to change over. All right, so we've taken care of our energy in, our energy generation term. This is all here, our energy out. And it's going to be equal to that energy storage term that we just defined. And that is going to be, of course, the density times our control volume, dx, dy, dz. Why? Because that gives us a mass, and that's going to be times our heat capacity and the change in temperature, right? Our change in temperature with time. And we just talked about that from the equation that I had written up here. And so here we have all of our terms now in our energy conservation equation. And now what we're going to do is put a little bit more beef into our qx, qy, qz terms to describe what's going on in this control volume. And then when we do that, we'll be able to cancel some terms out and simplify this long equation quite substantially. So let's go ahead and do that. All right, here, so we're going to be working with Fourier's law, but first, I forgot to point this out, but we actually can already cancel a couple of terms. So right here, I see a qx, a qy, and a qz. And over here, of course, we have the negative qx, negative qy, and negative qz. So we can already simplify this a little bit, and let's go ahead and cancel these and make our equation a bit shorter here. Qx, our qy, and our qz, they all cancel out. So this is going to be rewritten here. Energy generation term. And this cancels out, so minus our partial temperature with respect to x, dx. All right, minus our partial t with respect to y, dy. And of course, our partial in z. Easy. All right, and that's still going to be all equal to our energy storage term. Rho dx, dy, dz. Mass times our specific heat times our temperature change with time. All right. So now let's get into Fourier's law. All right, so yeah, now we're going to talk about Fourier's law. And I have Fourier's law in the general form written up here, which is Q equals negative K gradient of temperature, with negative K just being equal to some arbitrary thermal conductivity constant, depending on the medium. So we don't have to worry about that too much. And the gradient of temperature, we're going to think about that as our change in temperature with respect to one of our axes times the actually control area. So if you don't know what that means, I'm going to show you here and use this diagram to explain that a little bit. So let's do it for our x first. So we're going to write our energy in term for the x direction, qx, now using Fourier's law. All right, it's going to be equal to some arbitrary negative k, negative thermal conductivity constant, times our gradient in temperature. Well, that just means our change in temperature with respect to x, all right, with respect to x, because we're going in the x direction, times now, we need to think about where this qx is going through. And if you look here, it's going through on this, going through this surface, which is defined by dy dz. That's the area of this surface, and that's what it's going through. All right, so that's our gradient and temperature term right there. So let's multiply that by dy and dz. Dy and dz. All right, and once again, that's just our area, our control area, if you will, that our energy is going through. And we're going to do that for each term. Qy equals some negative constant there, thermal conductivity constant, change in temperature this time with y. And now let's see where y is going through. So this is our y, and it looks to me like it's going through this surface right here, which is dx here, and dz. So we'll just call that dx times dz, and that's the, once again, that's the surface it's going through. One more time here, let's do it for qz as well. Negative thermal conductivity constant, our change in temperature in z. And where's z? Well, that's easy. It looks like dx, dy is the surface that it's going through. All right, so this is that area, dx and dy. Now what we're going to do is, since we have equations for qx, qy, and qz, we're going to plug them in to here. All right, so if you were getting concerned when I was writing this equation, I was too. I was looking back at it, and something was not quite right. And that's for, of course, each of our times we put our energy outflow terms into, we put temperature. And this is not temperature. This is supposed to be simply the change of our heat transfer rates with respect to their respective axes. So this is this is x, so that's with qx, qy, and then qz. All right, so I had put temperature here. It's not supposed to be temperature. These are all supposed to be q, which of course is our energy transfer rate. So qx, qy, and qz. All right. And that becomes important because the whole reason we did this whole Fourier's law thing here is because we want to be able to plug this into each of these partial differential equations so that we can get our heat diffusion equation overall. So now that we have it actually written correct, let's go ahead and plug these in. And let's do that now. So these are our things we're going to be plugging in. I don't know if I have enough room. We'll try it. All right, so first we have, of course, this is not changing, our energy generation term, dx, dy, dz. All right, minus our partial with respect to x times, all right, we're doing this for our qx first, so we're simply subbing in for this qx that we just defined. Negative thermal conductivity constant, change in temperature with respect to x. This time it is our change in temperature. And then dy dz. We jumped the gun a little bit earlier last time, but that's okay because we caught it. And so all this is my qx, and you see right here we multiply it by dx still, our differential axis thing. All right, and we're just going to do that for the rest of these terms here. Let's see, partial with respect to y. Negative thermal conductivity constant, change in temperature this time with respect to y, and that's for dx dz. That's that plane. All right, and then finally one more time for z here. And we might run out of room, but that's all right. Oops. Partial with respect to z. This is going to be negative thermal conductivity constant, our change in temperature with z. And then our control area is dx dy. And oops, I forgot on this term. This is dx dy here. Dx dy. And I forgot, of course, we're still multiplying that by that dy from up here. So that doesn't go away, so we still have that. And the same thing is true here. We're multiplying that by our dz. And that is all equal to our energy. That is all equal to our energy storage term, which has been simplified a little bit here. And now we can, oops, I forgot. Let's see. This is, yep, I forgot our dx dy dz down here. Yeah, we haven't simplified it yet. Dx dy dz. Yep. Okay, so now what do we see? Well, we have all our terms in, and I see a dx dy dz here. I see a dx, a dy, a dz here. Dx dy dz, a dx, a dy, a dz, and dx dy dz. That's great. That means I can cancel all those terms out, and I don't have to rewrite all that, and can shorten this equation substantially here. So let's go ahead and cancel all those terms out, our control volume term, and after that see where we're at. So this is going to be just q dot, our dx dy dz cancel there, minus our partial of, with respect to x, my dy dz dx cancel there, so this is just now a negative thermal conductivity constant with our change in temperature with x, not 1 with x. All right, and we're going to do that for the rest of these terms here. Same thing, partial with y, negative constant, partial temperature, dx dy dz cancel, dx, oh, this is supposed to be a z, a little y there, that's supposed to be, or no, I'm looking at the wrong, this is supposed to be a, yeah, yes, this is supposed to be a z, I accidentally put a little y there. All right, so dx dy dz, those all cancel. Our change in temperature with respect to y is what we're left with, minus, one more time for our z here, for our z-axis, a negative thermal conductivity constant, change in temperature with z. And now that's all going to be, I don't like that parenthesis, that's all going to be equal to our energy storage term. That control volume cancels out, and we're just left with our heat capacity times rho times our change in temperature with respect to time. It's supposed to be a rho here. I don't know if I have that. So, yep, this is all we're left with here. Rho. And there you have it. So looking at this now, what we have actually done is we have simplified it enough. And this is actually right here, our heat diffusion equation in its general form for Cartesian coordinates. So this is actually the final answer here for the heat diffusion equation. We derived it using Fourier's law, and this conception here of our control volume. We understood that our energy conservation equation was going to be governing everything because energy can't be created or destroyed. So we accounted for all of those terms, plugged in what we knew. We made our energy outflow terms more rigorous by doing a Taylor series expansion, which aided in canceling some things out and shortening our equation. And so now we are left with this. All right, so while we did find the correct answer for our heat diffusion equation, we actually can simplify it just a little bit further here by noticing that we're minus a negative here. Our negatives are being multiplied. So, of course, that's just going to be a positive. And let's go ahead and do that. It'll make it a little bit prettier here, a little bit prettier and simpler. And of course, now this is the general form of our heat diffusion equation for Cartesian coordinates. So now let's talk about what it's saying. So this is saying that the net rate at any point in the medium, the net rate of thermal energy transfer by conduction plus the volumetric rate of energy being generated is just going to be equal to the rate of change of thermal energy being stored within the medium, within the volume. All right. So, and we got that by using our conservation of energy equation. And so doing this, we see that our energy is conserved. We can use it to describe what's happening within the medium. We did a Taylor series expansion in order to simplify and cancel some things out for our energy outflow terms. Fourier's law was used to elaborate on our Qx, Qy, Qz energy in terms. And of course, we remembered how to describe our energy storage and energy generation terms using our equation for what energy is equal to and describe those appropriately. And there we go. There we have it. That's our general form of our heat diffusion equation for Cartesian coordinates. So next we're going to work on spherical coordinates. It's going to be a little bit longer, a little bit more complicated due to the geometry, but it's going to be the exact same thought process. So we're going to go ahead and do that now. All right, so now we have derived the heat diffusion equation for Cartesian coordinates. So now we're going to do it for spherical coordinates. And once again, we're going to be following pretty much the same thought process, but for a different geometry this time. So I'm going to take you over here, and let's take a look at what I've set up for us. So right here, this is supposed to be a chunk of a sphere. It's not very well drawn, but it does get the idea across. This is a chunk of a sphere. And this is our control volume that we're working with this time, whereas last time for Cartesian it was more of a cube. And so how we have to think about this is we have a sphere, and in the middle we're going to cut across down a phi angle and across a theta. So down a phi, across a theta, and of course the sphere has some thickness r. And that is what is going to actually make up the three-dimensional geometry of what we're working with for this. So let's explain what's going on here a little bit. First of all, dr represents that thickness. That's the easiest part to understand. It's just how far that sphere's radius goes out in terms of the thickness of that medium. And so the biggest difference between our Cartesian and our spherical is that we cannot just call this d phi and d theta, where we could call this dz and dy like last time. And the reason we cannot do that is because these are angles, and so angles really don't tell us anything about the actual distance. And if we're doing a differential, we have to really deal with distance. A volume cannot just be an angle multiplied by a distance. It has to be three distances here if we're going to get our actual volume. And so a way to think about this is like an angle that for an astronomer, say, he's looking at the sun, or let's say the moon. Probably shouldn't look at the sun. He's looking at the moon, and he wants to describe, how many, where to look at it. And he says it's 30 degrees above that hill there. Well, 30 degrees is while true, can massively represent massively different distances. If I'm talking about this distance, well, that could be 30 degrees, and that's like an inch. But if it's like over the hill, that's miles and miles and miles of distance. So the farther out you go, the longer your distance between two things is going to be. While the angle itself will still be the same. So that's why we really need to put these in terms of distances, in terms of length, and not just leave them in terms of angle. So to do that, here's what we're going to do. We recall that the formula for arc length is S equals R theta. All right. So that means our radius, whatever the length is of our radius, times our angle, and that's going to be equal to our arc length. So our radius times our angle is actually now going to put it in terms of the distance, right? So that's pretty easy to see. That's what we did here. The distance here is R times d phi. And to get a better picture of that, in case it's still not clear, we're going to look at this axis here that really makes it a little bit easier to understand why it's r times d phi. If we're looking at this, you know what? I'm going to break this down in the next part. So I'm going to get us a better view here. All right, so the reason I stopped here is I was getting confused by this. What I actually did, if you notice, I wrote r d phi here. And that is incorrect because looking back at our axis, this is theta. It's going down theta. So it has nothing to do with phi for this axis. So this was supposed to be a theta, rd theta. Rd theta. All right, so once again, that's because the angle we're working with here is theta, not phi. So that clears that up. So a helpful way of looking at this is like a projection. And so we see that your radius goes out here, r, and it goes across some angle theta. Well, then that arc length is just going to be, equal to r d theta, all right? That's easy enough to see. So that takes care of our dr. That takes care of our r d theta. Now you're saying, well, what about this one, r sine theta d phi? All right, and this is the weirdest one, but it's not too bad. Once again, let's view this as a projection. And we see here, if this goes r out, well, then this would have to be down here, if we project it, r sine theta going across some d phi. Let me say that again. R sine theta across d phi, because this r times sine theta would be this distance. You can see that there. All right, and we know that we're defining phi as how far the angle is going across. So that this arc length is equal to this radius, which was r sine theta, times this angle, d phi. All right, so it's still radius times the angle. The radius is just now defined not as r, but as r sine theta, because that's what it would be in this direction. So that's easy enough to see, and because of that, this length here is going to be defined as r sine theta d phi. All right, so let's move it back here. Once again, we're going to be using our conservation of energy equation as our governing equation to sort of start with this. So let's go ahead and walk through that again. It's going to be the same logic as last time, but let's walk through it one more time here. So I see I have a bunch of arrows going into the system here, and I see I'm going to put an arrow here just to make that more clear. Arrow for our QR. So we have a bunch of arrows going into the system, and of course, once again, that represents our energy that's going in. All right, our energy going in, energy that's going in. And once again, we have energy generation and energy storage terms being described in the medium. Well, we know that our energy generated is going to be added to the energy that's going in. So we'll just go ahead and add that. Our energy stored, well, once again, we know that that is going to be lost. Some amount of energy is going to actually be stored in the medium. And if it's stored, well, then it can't be coming out. So we're going to subtract the energy storage term. Energy storage term. And that's all going to have to be equal to the energy that's going out, because there can't be any new energy that's created or destroyed. So everything accounted for, the energy coming out has to be equal to that. And so there we go. It's the same equation as last time. Only thing that's changed is our geometry, but the conservation of energy equation remains the same. So I'm going to rearrange that real quick, like we did last time. Our energy in plus our energy generation minus our energy out, moving it to the other side, equals our energy storage. And this is the equation we're going to work with when we're plugging in terms. And it's going to be our governing overall equation for how we derive the spherical coordinate heat diffusion equation. So we're going to go ahead and do that now. I'm going to break down some of these terms, and let's get to it. All right, so first thing that I want to do is to define each of our Q terms this time. QR, Q phi, and QR, Q phi, and it should be just Q theta. Apologies, that should just be Q theta going in. We're going to find QR, Q phi, and Q theta using Fourier's law. Also, quick note, I think I might have written E sub G there as energy out. I think I said one thing and wrote another. But energy in plus energy generated minus energy out equals energy stored. All right, so let's go ahead and define some stuff here now with Fourier's law. So once again, let's recall what Fourier's law is. Well, our Q, our heat transfer, is going to equal negative K, some thermal conductivity constant, times the gradient of temperature. All right, so let's apply that to our geometry here. So let's start with QR. So our heat transfer in the R direction is going to be equal to some negative K, negative thermal conductivity constant, times, well, it's going through it's going through our R direction here, so the change of temperature with R, change of temperature with R. And just like last time, we're going to look at the control area, the actual surface that this is our QR is passing through. And well, that's not too hard to see. That's going through this surface, r sine theta, r sine theta d phi, r d theta. That defines the area of the surface we're passing through. So let's multiply it by that. I'll just call that r squared since we're multiplying those r's together. And so that'll be r sine theta, d theta d phi, d theta d phi. All right. Not too bad. Let's go now to our Q phi. Q phi. All right, so once again, some negative thermal conductivity constant, easy enough. Our change in temperature now with, well, let's look at phi. Where is our phi going through? Well, our phi is in this direction. And we talked about how we can't just use an angle for a differential because it's not going to make any sense. The distance changes, and so we need to actually put a distance with this angle for this equation to make sense. And that's what we did here. So it's just going to be our r sine theta d phi. It's not going to be d phi. It's going to be r sine theta d phi because we need it as a distance. So r sine theta d phi. All right. And so now let's look at the area it's passing through. Well, our Q phi seems to be going this way, which is defined by r d theta and dr. So we'll just call that r d theta dr. R d theta dr. All right. One more time here, we'll do it for Q theta. Negative thermal conductivity constant times our gradient of temperature, which is going to be our change in temperature. with, now where is theta? Our q theta is right here. It's going this way. It's going up through an angle theta, but we need a distance. Once again, we've already done that, so it will be r d theta. It will be r d theta. All right. And what area is it passing through? Well, it looks to me like it's going through that distance, which is defined by r sine theta d phi, dr. That's the area it's going through. So we'll just say r sine theta, d phi dr. d phi dr. All right, so we just used Fourier's law and described all of our energy in terms that are going to be added together using that. Let's go ahead on to the next part now in our overall conservation of energy equation approach. All right, so the next thing that I want to do is, now that we've taken care of our QR, Q phi, Q theta, our heat transfer going in, let's take care of our heat transfer rates coming out now. And we're going to do pretty much the exact same things we did for Cartesian coordinates. So let's see where I have some room. I'll do it down here. Our Q, let's do QR first, our QR plus DR. All right, our QR plus DR, energy transfer rate coming out. Well, once again, we see that that's just going to be what it was before, the rate before, plus the change actually of that R, of that QR, of that heat transfer rate, over that distance dr, over that distance r, and that's going to be multiplied times the distance is allowed to change over, dr. Exact same thing. Let's talk about it with the speed analogy again. My speed after going through this is going to be equal to what my speed was before, plus the acceleration times the time it was allowed to accelerate. Heat transfer now. Our heat transfer rate is going to be at location r plus dr is going to be equal to what it was going in, plus the amount it was allowed to change by in that medium, times the distance it changed over. All right? So we're just doing a Taylor series expansion for these terms again, and that's how we're going to define these. So we'll go ahead and do that for our second two axis directions now. So we'll do, let's do q phi next here. Our q phi plus d phi direction. All right, so that is going to equal to q phi, where it was going in, plus our change in our q phi, our heat transfer rate, over a distance phi. Now, this one, actually, it's not a distance, it is an angle, but we can do this because, once again, we're dealing with q phi. And so you can kind of think about it as the q phi already has sort of a distance built into it. We are fine, the units will work out, and we can just do it over this angle, because that's what we're carried about for this time. But for these, we needed to have a distance because it wasn't already built in. So we're going to just leave it as that times, of course, the angle it's allowed to change over phi. And one more time here for our q theta. Q theta, all right, plus d theta position is going to be equal to what it was at the beginning, plus the amount it changed over the angle. How it changed over the angle times the angle it changed over d theta times d theta. All right. So now that we've done our Taylor series expansion and described these terms in more detail, we're going to go ahead and start working with our energy conservation equation. And what we're probably going to do, because this is a little bit longer, and to make it a little simpler, we're going to deal with first our energy in minus our energy out. All right. We're going to deal with our energy in minus energy out and figure out what this minus this is before we plug everything in. So let's go ahead and do that now. All right, so let's go ahead and deal with our energy in minus energy out terms here before we start working with the overall whole equation. And just like with Cartesian coordinates, we notice that our energy in, which is going to be, say, for the r direction, QR, minus our energy out, well, that's QR plus dr. QR plus dr. Well, that's going to be equal to our QR minus our QR plus dr. Well, what's that? Well, it turns out that is QR plus r, partial r, over r dr. All right, so right away, what we notice is we have a QR minus a QR. And that saves us a lot of headache. We can go ahead and just cancel those out, and it's just going to be left equal, so it should be minus that minus is distributed. It's just going to be left equal to that minus our partial of QR over partial R times dr. And that's going to be like that for each of our terms here. So energy in minus our energy out for each term, including our Q phi, Q theta, oops, minus here our Q phi plus D phi, location Q phi plus D phi, and location Q theta plus D theta is going to just be equal to, well, we'll just cancel out our Q theta, and we'll just be left with our negative partial here, which for Q theta is going to be negative our partial Q. I'm sorry, for our phi, it's going to be negative partial Q phi over D phi times D phi, oops, times D phi. That should be a partial there. And likewise, it will be the same for theta. Partial theta, D theta. All right, so right here we have our energy in minus our energy out terms dealt with and defined just by doing simple cancellation that we got from defining using Fourier's law as well as our Taylor series expansion here. And that's easy enough. Next thing we're going to do is we're going to use our Fourier's law to plug in our QR, Q phi, and Q theta, our heat transfer rates in those axis directions, and we're going to actually plug it into each of these. It's a little bit long, so I'm going to clear out some space, and then let's do that. All right, so what I want to do right now then is start putting all of our terms together here. So let's go ahead and write out the rest of our energy conservation equation here. All right, so we have energy going in minus some energy coming out, which we just defined, plus an energy generation term is going to be equal to the energy storage term. All right. So using this, let's go ahead and plug all our relevant things in. So we just defined our energy in minus energy out as these up here. So let's go ahead and do that. So do it down here. That's going to be a negative partial Q here, R over our partial R, dr, minus Q phi, partial phi, d phi. And once again, we know what all these things are, and we define them. Q theta, partial theta, times d theta. All right, so that's our energy in minus our energy out. Let's go ahead and do our energy generation. We'll just leave that as EG right now. We'll get to more of that later. Equals energy storage. All right. Right now, I just want to plug in some things. So let's go ahead and do that. Where we're going to plug in our Q, R, Q phi, Q theta into our equation down here. So that's going to be equal to, I'm still on the board here. Yep, that's going to be equal to negative. Actually, you know what? Looking at this right here, we see each of these terms is negative. But also each of our Q's here have a negative term. So I'm a positive guy. I don't like to have a lot of negatives. So we're just going to go ahead and drop that negative when we sub in that K because we know it's going to be two negatives multiplied by each other. It won't be a positive anyway. It'll just save us from writing a whole bunch of negatives for no reason. All right, so our QR, so our partial here, partial R. What's QR? Well, that's going to be K, our thermal conductivity constant, times our gradient temperature. So that's a change in temperature with R times R squared sine theta, d theta d phi. D theta d phi. And remember, all that is going to be being multiplied by our dr here. All right, let's go on to the next term. Partial with respect to phi. All right. And what we're going to do is plug in our Q phi there, which I said we're going to make that a plus, so thermal conductivity constant. times our gradient of temperature, which is of course our change in temperature, this time with our sine theta d phi, our sine theta d phi, times the area it goes through, which is defined by r d theta dr, r d theta dr. All right, one more time here. We're still on the screen. We are. All right, so change slides over here, and we're going to define this as our partial here with respect to this time theta. Some thermal conductivity constant, our gradient of temperature, which is our change in temperature this time by r d theta, that distance there, r d theta. All right, and what we're going to do is multiply that by this area, r sine theta d phi dr. Oops. D phi dr. All right, and so we plugged all of our Q's in now, and then plus, of course, our energy generation, equals our energy storage. All right, so it's kind of long, but we're going to start doing some things that will allow us to cancel out. So we're going to define our energy generation and energy storage terms next. But right now, this is the state of the equation. So we'll get to that now. All right, so first, actually, before we address our energy storage and energy generation terms, let's make this a little bit more helpful to us later on and pull out terms within our partials here. The partial itself does not depend. So, like for partial r, we can pull out sine theta, d theta, d phi, because of course they don't depend. It does not depend on r. Also, a quick note is we wrote all our terms here for Q, but I did forget the. I remember the dr here, but I forgot the d phi for this term and the d theta for that term. So we're going to write that in now and then start pulling out some stuff here. So this should be, let's see here, dr. Try to squeeze it in here. dr, and then of course all that is going to be times our d phi, which we forgot. And same thing with this one here. Plus our energy generation equals our energy storage. Plus our energy generation equals our energy storage. But we forgot our d theta there. So we'll just put that there. And that's no problem. All right. Now what we're going to do, just checking here, d theta, d phi. So yeah, now what we're going to do is start pulling out some stuff that will help us cancel on terms of it. So make sure we're pointed down enough to use this. And all right. So let's go ahead and do that. So first thing we're going to do is, for example, for this. This is going to be, well, I see this sine theta, a d phi, and a dr. All that can be pulled out because it does not depend on a dr. So let's go ahead and do that. Sine theta, d theta, and our d phi. And that's going to be times our, and our dr as well. And this will be times our partial respect to r. And we'll just leave r squared in there. We'll leave our k in there. And it's like our partial temperature with respect to r. All right, so as you can see, we just pulled out everything that did not depend on our r there. So we can write it in a different way there. And I'm going to go ahead and stop here. All right, so this term is good here, and I'm going to do the next two now. And right here, we can see that the things that don't depend on phi here, so we can pull out our r sine theta And we have here r d theta dr d phi. So we can pull all that out. So that'll be r sine theta, and sorry, that should be in the denominator because we're pulling it out from this denominator. So that should be r sine theta, and that's the denominator. And we can also pull out r d theta r d phi, r d theta dr d phi. And when we see that, when we look at that, well, we got an r in the numerator and an r in the denominator. So let's just get rid of that and make it a little simpler here. They cancel each other out. And so we've pulled that out, and that's going to be multiplied times our partial respect to phi. And now that's, we still have, depending on that, make that a little cleaner there. So we still have our k, which we're just going to leave in there. And we have our partial of our temperature. We pulled out our r, we pulled out our sine theta. We still have respect to phi now. And I think that's everything. Yep, so that's a little bit cleaner, a little bit simpler now. One more time here. So what are we going to pull out? Well, this is our with respect to theta, so I can pull out this r, and I can pull out this r sine theta d phi dr. So let's go ahead and do that. Let's go ahead and do that. You know, actually, we cannot pull out that sine theta because this is theta. So we do leave that. We do leave that theta there. So we'll just pull out r d phi dr, and then of course the theta is outside parentheses. So it's going to be r. Cannot pull out the sine theta, but we can pull out the d phi and the dr and the d theta. It's because it's outside. And we can pull out this r. Well, once again, we see these two r's cancel, so we'll just write down that and not have to worry about a fraction. I'm going to rewrite that as d phi dr d theta. D phi, dr, and d theta. All right, so we just pulled all those out, and they're going to be multiplied by our partial with respect to theta, keeping k in there, keeping our gradient of our partial temperature with respect to the theta angle. And looks like the only thing left in this is, of course, going to be our sine theta. Awesome. Plus energy generation equals energy storage. All right, so we just simplified a few things there, which is going to make it a little bit easier later on. So I'm going to end it there, and then we'll move on to the next part here. All right, so now what I'm going to do is talk about our energy storage and energy generation terms, which we have hitherto not addressed yet. So we still have our EG and our EST to deal with, and let's deal with those now. Let's deal with our energy storage term first, all right? Well, we remember we need a mass times a we need a mass times a specific heat capacity times a gradient of temperature. That's going to be equal to our energy. Remember that from the definition we had when we were doing Cartesian. So let's go ahead and do the same thing. It's the same thought process. So we need a mass. Well, we're going to get that. Well, let's take a density times our volume. Now, because this is a control volume, a differential volume, each of these is infinitesimally small. We can just approximate this as a cube, and the volume will be accurate. All right, so we're just going to multiply those three axes by each other. So that's going to end up being r squared sine of theta times d phi, and then d theta dr. Theta and dr times some heat capacity Cp. So this is our mass times some heat capacity Cp. And of course, now the only thing left is our gradient of temperature, which is just our change of temperature with time. All right, simple enough. Finally, now let's do our energy generation term here. And our energy generation is going to be equal to, well, some arbitrary volumetric heat rate times, once again, our volume, which we just described as this because we're approximating it as a cube because it's infinitesimally small axes here. So r squared sine theta, d phi, d theta, and dr. All right. Next thing we're going to do is plug these in down here, down to this equation we just worked on, and start canceling some stuff out and making it a little bit cleaner, but we're almost there. All right, so what I did here, because we were running out of space, is I just rewrote that whole equation we had on the bottom of the board on the adjacent board up here at the top. So what we're going to do now is plug in our energy storage and energy generation terms that we just defined. And so let's go ahead and do that. So I have it on this other board over here, so I'm just going to copy it now. So that's going to be, for our energy storage, going to be rho r squared sine theta d phi d theta dr. d phi d theta dr, some heat capacity Cp, times, of course, our change in temperature with time. All right, and that's plus our energy generation, that's of course equal to our energy generation, which is some volumetric heat rate per unit volume times our unit volume, r squared sine theta d theta d phi dr, sine theta d theta d phi dr. d theta d phi dr. So I could go ahead and just rewrite plus this, and do that. But looking right here, we see that each of these has a d theta, a d phi, and a dr. D theta, d phi, dr. Up here, d theta, d phi, dr. D theta, dr, d phi, d theta, d phi, dr. So we see every term here has that. So I'm going to go ahead and just cancel it out here and then rewrite it. Just save a little time there. So let's go ahead and do that. So we can cancel out our d theta, d phi, dr. So that's going to be equal to now rho density r squared, so density times r squared sine theta. These cancel out. Some heat capacity times our rate change in temperature with time equals volumetric heat. Volumetric heat rate times our volume, which is now, since we cancel that out, just r squared sine theta. All right, nice and short there. Let's step over here. Plus, all right, so my d theta, d phi, dr cancels there, so that's just plus sine theta times my partial with respect to r squared k temperature with r squared k temperature with r. Yep, those all cancel. Plus d theta, d phi, dr, they all cancel, so we're just left with actually 1 over sine theta. 1 over sine theta times our change with change of phi of k partial temperature with phi. Right? Cancel those. Left with that, left with that. All right. One more time here. d theta, d phi, dr cancel. So we're left with partial respect to theta of sine theta k partial temperature with theta. All right, so this is really close to the end here. One thing we're going to do to put it in the general form is just divide by r squared sine theta for each term. And then we should be there. So let's go ahead and do that. So rho Cp, so heat capacity, of course, and our change in temperature with time. All right, we divided by r squared sine theta. Right, that goes away. Q dot dividing by r squared sine theta. Well, that's great because now we're just left with q dot, so we don't have to worry about that. Dividing by r squared sine theta. Sine theta's cancel. I'm left with 1 over r squared. 1 over r squared times my partial respect to r of r squared k partial of our temperature with respect to r. And you see, it's tempting. We want to pull that r squared out, but we can't because this is actually a partial derivative with respect to r, so we got to leave it in there before pulling it out so it can be evaluated. But the rest there is good. We did cancel at least one thing. Plus 1 over r squared sine squared. of theta. All right, so we see we're dividing by r squared sine of theta, so it's going to be r squared times sine squared of theta now because we can't cancel anything, and we'll actually be multiplying two sides by each other. That's all right though. And that's going to be partial with phi of our thermal conductivity with changing temperature with phi. All right. Oops. And now we got one more term here. Plus, and we're dividing by, what is it now? R 1 over, we're dividing by r squared sine of theta. Well, we can't pull that sine theta out, so we're going to be left with another denominator here where it's r squared. This time it's just sine of theta. There's not one denominator. All right. Times our partial with respect to theta of sine theta. Couldn't be pulled out because it depends on theta. Okay. Our change in temperature with theta. All right. So, believe it or not, this is actually the general form of our heat diffusion equation for spherical coordinates. It's saying the same thing as our heat diffusion equation for Cartesian coordinates was, which is just to say that the net rate of thermal energy transfer by conduction plus the volumetric rate of energy generated is going to be equal to the energy storage rate. All right, it's going to be equal to the change of the rate of change of energy storage stored within the medium. That's all this is. We define each term. We know what everything's talking about here. And it all goes back to our geometry that we had over here. And it's just defining using the energy conservation equation, it's just defining what the heat is going to behave like in this medium. So that was it. We just defined the heat diffusion equations for spherical and Cartesian coordinates. We did a lot, but I think we explained all of our terms that were relevant, and then we got to cancel some things, which was nice. And that's all there is. So thank you for watching.